Okay, guys, vodcasting the solutions to lab 3.1. Do want to apologize. I know I am testing out again another software program, so I am aware that there's this big thing that says ScreenFlow or something ridiculous like that in the middle of your page. So let's just bear with that for today, and Mr. M will come up with the money necessary to pay for this. So my name is Ramsey, and I'm part of all the blocks. Yay! Woo! So for pre-lab notes, really in the pre-lab notes, I had you draw 3 different pictures, and everybody should have the same pictures drawn. And actually, you know what? I'm not going to do this part because everybody drew those same pictures when I graded the lab. I did not mark that part down at all. So we are going to move on to the next part of the lab. Here, it's basically just the instructions. Everybody kept their data in these little charts here. So this is where your data is. Yay. And we're going to go up here, move forward. Move forward up here, this little pen guy. Data was kept here as well. Okay, more data. Let's see if right-clicking can bring me back my pen. Can right-clicking bring me my pen? Nope, I gotta go back and do it here. Okay, more data. Now here's the part that I really want to go over. Most people miss prop points on this lab simply because they didn't label the axes. So I wanted you to label this with temperature, and I said put it as degrees Celsius, and I wanted you to label this with time and put it with seconds. Now we did the cooling curve first. I'm going to draw the hypothetical thing. Most people should have seen something that kind of looked like this, plateaued out to an extent, and went down. Okay? Now what we're really paying attention to here is this plateau. This plateau is the liquid to solid equilibrium line. This is where freezing was happening. Here, all liquid. Here, solid, and at this point right here it's a liquid, but it's a liquid below the freezing point, so that is where it is supercooled. It's a supercooled liquid in that case. So let's hypothetically identify this point right here as, let's say, 48 degrees Celsius. So that is the plateau. That's going to become important later on here in these questions. So, according to the graph above, what was the freezing point? So any freezing point, we are looking for the plateau. Did I spell that correctly? I think there's an A in there. I don't know. Somebody tell me how to spell that tomorrow. We're looking for the flat place. And explain your reasoning. So we are going to say it was around 48 degrees Celsius. This was the temperature at which there was a plateau. I think that's how I spell it. I think this is an A. Okay. Yay. All right. For the heating curve, again, we're going to label it exactly the same way we did before. We got temperature, we have degrees Celsius, we have time, and that's going to be in seconds. Now, in this case, we're working in the opposite direction. So, ideally, we would have seen something that looked like this. This is the solid region. Here is the region we're really looking excuse me, here's the region we're really looking for at the solid to liquid equilibrium line. This is where melting is happening. And here's where it's a liquid. Since this is a heating curve, this is the superheated region. Superheated because you notice this region right here, it's not supposed to be a solid. Okay, so clearly labeled that whole thing. Now let's say that really this should be the same temperature as before. Why don't we, let's just call it the same temperature since this is the key. Because the melting point and the freezing point are really the same temperature. So according to the graph above on the other page, ooh, let's go get my little pen. Hey. What's the melting point? So C answer to cooling curve. So it should be the same answer. Let's go back and take a look at the cooling curve answer. So I believe, no, it's on the next page. Okay, 48 degrees Celsius. Okay, this was the temperature at which there's a plateau. Same answer for the heating curve as for the cooling curve. Oop. I need to go back. All right. So when a graph like this pops up, we definitely want to label the regions first. Here is the label that pops out to me. That looks like that is the plateau. This is a cooling curve. That's going to be the phase change. It asks me if the melting point can be determined from this. I'm going to then circle C, because that is the melting point. Let's go back and look and see at which temperature does that happen. You know, it looks like the melting point of naphthalene here is around, yeah, around like 85, 84 degrees Celsius. Okay, so we got it. Same thing with this. This is also a cooling curve. So let's take a look at it. Again, here's the plateau that we're really concerned about when doing this. So I'm going to pull up this. All right, so for this cooling curve, the solid and liquid coexist. Where do they coexist? They coexist when it's melting. So this is a fancy way of just saying there's a phase change. In this case, it's freezing because it's a cooling curve. Okay, so they coexist at along the line R and S. Okay, so it can't be A. Q is not on the line R and S. It is point R only. Between Q and S, it's tempting, but Q is definitely not on that line. Notice Q is right here. Line is up here. All points between R and T. T is not on the cooling curve line. So the answer in this case is going to be B. All right. So it looks like here, got another graph? Okay, so the first question says the graph below shows the temperature as a function of time. So question 16. When the average distance between the particles is the greatest, that's when it's going to be in the gas phase. So here it's a solid, here it melts, here it's a liquid, here it boils, here it's a gas, happens at point T5. So E. A time when the temperature is between the melting point and the boiling point. So the melting point is the first plateau, and the boiling point is the second plateau. So here is the time in between T3, C. Have a good day.